When you clicked on this video, you probably wondered, why don't modern airplanes use gasoline like cars, but instead use kerosene? Behind this seemingly ordinary fuel lies a complex technical system involving safety, temperature, altitude, and how massive jet engines operate in sub-zero temperatures. In today's video, let's explore how kerosene is made to understand why the aviation industry chooses kerosene over gasoline. But before we understand why kerosene is suitable for jet aircraft, we need to go back to the beginning. How is this fuel actually made? Before kerosene could appear inside the wing of an airplane, humans first had to find crude oil deep underground. Oil companies had to look through the ground using massive seismic surveys. Special vehicles in the desert, or ships at sea, would create extremely powerful vibrations that traveled deep into the earth. These vibrations would reflect back to the surface and be recorded by sensors. Then, supercomputers would transform all this data into 3D geological images so that engineers could find potential oil deposits. If an area appears promising enough, companies will begin setting up exploratory drilling rigs and drilling thousands of feet deep underground. Once the drill bit reaches an oil-bearing formation, the well walls are lined with massive steel pipes and sealed with cement to stabilize the surrounding rock layers and prevent pressure leaks. At the wellhead, engineers install a blowout preventer, a multi-ton safety valve system capable of sealing the well completely within seconds if dangerous pressure levels are detected. In many offshore oil wells, underground pressure can exceed 10,000 pounds per square inch. Even a small loss of control can lead to a catastrophic oil and gas blowout at sea. Once everything has been reinforced and secured, crude oil extraction can finally begin. At first, natural underground pressure may be strong enough to push the oil to the surface on its own. But over time, engineers often need to deploy additional high-powered pumping systems such as electric submersible pumps, which can extract tens of thousands of barrels of oil per day to maintain a stable flow. However, what goes up isn't just oil. It's a mixture of crude oil, natural gas, water, and even fine sand. Therefore, it's passed through separator systems for preliminary separation and processing before being transported to the refinery. The natural gas is compressed and stored separately. The water is treated to remove oil and sediment, and the crude oil is further filtered to remove salt and impurities before being transferred to temporary storage tanks. Only after this step is the oil stable enough to be transported to refineries. After being separated and initially processed, crude oil is then transported to refineries via pipelines, tankers, or trains. The world's largest supertankers can carry over 2 million barrels of oil in a single trip. Inside these massive pipelines, oil is pumped continuously day and night, over distances of hundreds or thousands of miles. When crude oil arrives at a refinery, one of the very first major steps is heating the entire mixture to extremely high temperatures. The crude oil is pumped through massive industrial furnaces filled with long, winding steel pipes inside. Here, temperatures can reach around 700 degrees Fahrenheit, enough for most of the hydrocarbons inside the crude oil to begin turning into vapor. Crude oil usually spends only a few minutes passing through the entire furnace system before being sent into the distillation tower. However, crude oil is actually a mixture of many different components, and the important thing is that each of those components boils at a different temperature. That is why the purpose of heating crude oil is to prepare it for the next stage, where different types of fuels can be separated into individual products. After being heated, this mixture of vapor and liquid is immediately sent into a massive distillation tower. A distillation tower in a modern refinery can stand more than 150 feet tall and operates continuously day and night. Inside the tower, the temperature is not the same at every level. The bottom section is the hottest, while temperatures gradually decrease higher up the tower. As the hot oil mixture enters the tower, lighter hydrocarbons rise higher before condensing back into liquid form. Heavier components condense earlier in the lower sections of the tower. Gasoline is usually collected near the upper part of the tower. Diesel is collected lower down, while kerosene is extracted from the middle section. However, the kerosene just separated from the distillation tower cannot be used immediately. It still contains sulfur, water, and many impurities that can cause corrosion or affect the engine at high altitudes. Therefore, kerosene will go through several more processing and purification stages inside the refinery. First, kerosene is mixed with hydrogen under high temperature and pressure to remove sulfur. Then, the fuel is further filtered to remove water, microscopic metals, and remaining impurities. After completing the entire refining and treatment process, the kerosene officially becomes aviation-grade jet fuel, such as Jet A or Jet A1. The fuel is then transported through pipeline systems, fuel tankers, or tanker trucks to airports around the world. At many major international airports, jet fuel is even pumped directly through underground pipelines running beneath the tarmac to each individual aircraft gate. And only after this entire journey is completed does the fuel finally get pumped into the wings of modern jet aircraft. Now that you know how kerosene is made, let's find the answer to a question many people have always wondered. Why do airplanes use kerosene instead of gasoline? The first reason to mention is that kerosene is much safer than gasoline, especially when it has to be stored in massive quantities inside jet aircraft. The biggest difference comes from how easily these two fuels evaporate and ignite. Gasoline can produce flammable vapor at temperatures as low as around -45 degrees Fahrenheit. That means when an aircraft is flying at altitudes above 35,000 feet, where outside temperatures can drop below -60 degrees Fahrenheit, gasoline can still evaporate and ignite almost instantly from even a tiny spark. Kerosene, on the other hand, is far more stable. It usually needs temperatures of around 150 degrees Fahrenheit before it produces enough vapor to ignite. Because of that, kerosene evaporates much more slowly and is significantly less dangerous during storage and refueling operations. But with jet aircraft, safety alone isn't enough. When cruising at high altitudes, outside temperatures can drop below freezing. And on flights lasting tens of hours, the fuel inside the wings also cools down along with the outside temperature. If the fuel becomes too cold, tiny wax crystals can begin to form inside the fuel system. This can reduce fuel flow and affect jet engine performance. Therefore, kerosene jet fuel must be very strictly controlled for its freezing point to remain stable in extremely cold conditions at high altitudes. Additionally, kerosene is better suited to low-pressure environments and long, continuous flights. That's why this type of fuel has become the standard choice for most modern jet aircraft. The next reason lies in how jet turbine engines operate. Unlike car engines, which create thousands of small explosions inside the piston, jet engines need to maintain a steady, continuous flow of combustion for hours on end to generate thrust for the aircraft. Air is drawn in at extremely high speeds, compressed, and then mixed with fuel in the combustion chamber at extremely high temperatures. And this is where kerosene does it better than gasoline. Kerosene burns more steadily and is more suitable for the continuous operation of jet turbines. But interestingly, the fuel on an aircraft isn't just used for combustion. Before entering the combustion chamber, kerosene continuously passes through pipes, the fuel pump, and many hot parts inside the engine. In the process, it simultaneously absorbs heat to help cool part of the fuel system. In addition, kerosene is also oilier than gasoline, providing better lubrication for the moving parts inside the fuel system. Meanwhile, gasoline evaporates much faster and is much drier, making it less suitable for high-powered jet engines that need to operate continuously at high altitudes. And all those factors become particularly important for modern long-haul flights. An international jet might have to fly continuously for more than 10 or even 50 hours across the ocean without being able to refuel mid-flight. This means the aircraft must carry a huge amount of fuel right from takeoff. In this case, kerosene becomes more suitable than gasoline due to its stability and high energy density by volume. Simply put, it allows the aircraft to store more energy in the same space within the wings and fuselage. In addition, kerosene is also more stable during extended storage periods over many hours of continuous flight. That's why most modern jets are designed around this fuel for long-haul flights worldwide. Looking back at that entire journey, from oil fields deep underground to giant refineries, and finally the wings of jet aircraft, it's clear that kerosene didn't become the standard fuel for aviation by chance. It's safer, more stable in extremely cold environments, more suitable for jet turbine engines, and more efficient for long-haul transatlantic flights. If you found this topic interesting, don't forget to leave a comment, subscribe, and turn on notifications.